Oh, yay, we can start. I'm not going to talk about administrative stuff too much. We're still working through grading. We think the bulk of it is done, but there are some edge cases that we're still handling, like some quizzes. You should see the stack of quizzes that were in my office before I moved them to Wade's office. Every quiz that anybody took in this class ever, they were all in a pile in my office. It's like taller than you. But they're gone now. They're in Wade's office. Yes, go me. That's the process of moving. Okay, so last time we were talking about traversal, graph traversal, and we spent a lot of time and effort and cognitive energy talking about breadth-first traversal. I'm going to spend a lot less time and cognitive energy on depth-first traversal because I think you already get the point. You already get the idea that what we're doing is assuring ourselves of processing every vertex and every edge in a graph in an order that reflects a movement on the graph, as if we were moving on the graph. Mostly, sort of. Let's see. So, I'm going to start the discussion of depth-first traversal by showing you a movie. You never talk in a movie, and turn off your cell phones. Well, I'll let the movie mostly speak for itself. I'll get your feedback. You can review it afterward.
After King Minos of Crete defeated King Aegeus of Athens, he demanded that the Athenians send 7 young men and 7 maidens every year to Crete, there to be sacrificed to a savage monster with a bull's head and a man's body called the Minotaur. Aegeus' son, Theseus, volunteered to go as one of the 7 young men and kill the Minotaur. He told his father that on his return, he would replace his ship's black sails with white ones to let Aegeus know that he had succeeded. The Minotaur lived in a maze called the Labyrinth, from which no one could escape. It was designed by the master inventor Daedalus. When Theseus arrived in Crete, Minos' daughter Ariadne fell in love with him and gave him a ball of string so that he could find his way out of the maze. Theseus entered the labyrinth, slew the Minotaur and led the Athenians to safety. But on returning to Athens, he forgot to fly white sails, and his father, thinking his son has been killed, threw himself to his death in the sea, which thereafter became known as the Aegean.
Okay, there you go. That is our little attempt at multidisciplinary reflection of computer science across campus. That's our contribution to that effort. I used to kind of joke that I really enjoy Greek mythology, but I don't know that much about it. The main reason that I care about this particular story is that it helps me with the New York Times crossword puzzle. And but at that point, when I was making that joke, it had never really been true. But in one of the most cosmic events of my life, in 2011, after I gave this lecture, so imagine that I made the joke about, oh, it helps you with the crossword puzzle. That night, I went home and I did the crossword puzzle, and one of the clues was feature of the ancient palace of Minos at Knossos. And I was like, I don't know. I don't know Greek. I don't know Greek mythology very well. And I completely missed my chance at going, oh, I know this one. I had to get all the crosswords, and then I went, ah! So it really does help you with the New York Times crossword puzzle. The other thing it helps you with is being able to envision what depth-first traversal is like. The salient point of the story is the yarn. It's the yarn in the story that helped Theseus get out of the maze, that tells us sort of what a state of depth first traversal is. At any point, we have explored some avenue between the current vertex and the start. Now, our story is, though, that we will never really roll up the yarn. Rather, the yarn itself is going to denote the discovery edges through the traversal, and it will lay out the paths that we have navigated. All right, so let me give you a very, very quick overview of how depth first search works. Now, the way I want you to interpret this is the way I want you to think about it is to consider the structures that are in place in support of the traversal. Just like we had for breadth first search, those things are going to include a predecessor vertex for any location, a current distance between a current location and the start of the traversal, those P and D structures. We're also going to be concerned with labeling edges and marking vertices, okay? So all of those things, just as they existed for breadth first traversal, will exist here as well. I just might forget to point them out. If you forget what they are, I'm going to refer you to the last time's lecture where we covered it all much, much more carefully. Okay, so to start off a depth first traversal, just like for breadth first, you choose an arbitrary vertex. In this case, it doesn't actually matter too much where you start, whereas in breadth first you get a little bit of information, additional information. That is, the distances from the start to where you are here have no particular characteristic. They aren't necessarily shortest. All right, so we choose a starting point, and just like for breadth first, we set up a for loop over the incident edges, and our process is to stand at a vertex, look across, and ask questions of the adjacent vertex, one at a time, okay? So we're going to start here and query this vertex and say, hey, have we been there yet? And the answer is, why, no, we have not been there yet. So we consider that vertex to be our next vertex. Mark this as a discovery edge and do all the other bookkeeping that we might be interested in. And then we start the traversal again recursively from this vertex. Okay? And that's an iteration. That's the processing that happens at every stage of the algorithm. Now notice what we're doing here though. We left this for loop hanging. The for loop was going across all the incident edges and we took off. We're like, I'm out of here, okay? So there is this computation underway that we're kind of ignoring as we go off in search of the solution to the rest of our problem, okay? All right, so what do we do when we start a traversal? We set up a for loop. I guess I'll do it the same way. And then we process whatever happens to be the first vertex there, okay? In this case, we look across. We haven't been there before. So we mark this as a discovery edge, and we begin the traversal anew from here. Again, we set up the for loop, start in what we consider, somewhat arbitrarily to be the first vertex, to be the first incident edge, look across. We see a new vertex. We'll talk about what to do in the other case in just a second. We mark the edge as a discovery edge, and we begin the traversal anew from here. Okay, any question about that so far? Okay, I'm going to do this because you're going to be bored if I do it the other way. Okay? So I'm going to set up the for loop again. The first vertex that my for loop happens to get is that one. What should I do about that one? Nothing is right. Nothing is right. I was prepared. If nobody said anything, I was going to go, oh, you're all right. Nothing, that's right. It's really bad form to make a joke about the joke you were going to tell, right? Ooh, that's bad. Okay, so right. Anyway, you're right. We're going to ignore this vertex. We're going to ignore this edge and move on to the next one. What happens here? What's the story here? We yell across the vertex and it says, you've been here before. In the breadth first traversal, we would have called this a cross edge. In depth first, we happen to call it a back edge. Okay, so this is a back edge. The difference in the words is chosen because there are different characteristics in the edges themselves. Okay? And it is the subject of some study in 374 to ask about, well, what are the characteristics of a graph that has a back edge, you know, before a cut point or after a cut point, or several different questions that you can ask based on this back edge. So, but we're not going to do it here. And we're done with that one, okay? So we see that it's a back edge, and we say, okay, that edge is now done. And we move on to the next edge here. We look across. We haven't ever been there before, and so this one is a discovery edge. And we move on to here, okay? What's this edge? We set up the for loop. What's that edge? It's a back edge, that's right. Dunk, dunk, dunk. And, you know, I'm getting a little tired of this, and you probably are too. I will finish this one out, though. So what happens here is at this green vertex, it looks across, it sees a new vertex, and the edge is marked as a discovery edge, and this vertex, depth first search is called from this vertex. The for loop is set up here, and there's only one edge, right? And it gets ignored. So this is our first case in our example traversal here where we actually finish computation in one of the function calls. All of these other ones are just like a stack of unfinished for loops, or we don't know if they're finished. So we back out here. This kind of constitutes, you know, rolling back up the yarn effectively. We fall out of this recursion to here, and oh look, we're done with this for loop as well, right? And we fall back to here, and we would proceed onward with this one and then this one, okay? Now, there's one more observation about this that I want to make. Think about that execution of the file or function at that node. Okay, think about the depth first search called from the green one up there. We left it in the middle of its for loop. And on our journey, we changed how that for loop's going to play out. Because this time, now, a lot of those iterations are just going to get ignored, right? Anytime there's a back edge that comes in, we're kind of finishing some computation that we left hanging. All right, any question about that? And so that vertex up there is finished even though we never really finished its for loop. That for loop is going to finish trivially. Any question about that? Okay, so about those P's and D's here. We're still going to mark them the same way we did before, but this time they have less meaning for us. In breadth first search, the D's are the shortest distance between the start vertex and any other vertex in the graph. We have no such meaning for those distances in this structure. However, there are inferences that you can make about the structure of the graph if you keep track of not only the point at which you first visit the vertex, but also at the point where you finish processing a vertex. So if you label 2 basically times in your algorithm, then you can make inferences about how much of the graph sort of lives in that part of the traversal, and thus in that part of the graph. All right, so I think that was all I wanted to say about executing the algorithm. I won't take you through the rest of it. I'm going to trust you to be able to do that. All right, so this looks very, very similar to what you've seen before. Like last time, I want to focus first on this, and I want you to observe that it's a little bit different. In this case, we're not using an auxiliary structure like a queue to orchestrate the traversal. Rather, we're letting the call function stack keep track of where we were before we moved on. But other than that, it's kind of the same. This set v visited, set the vertex to visited, that was like me bubbling in the dots at every iteration, right? Here is the for loop. That's the little loop that I drew. And then this is appropriately processing each incident edge. The key part here is that we let ourselves get distracted. That is, we let ourselves make a recursive call right in the middle of this computation. Okay? Is there any question about that? The whole reason I didn't just replace queue with stack here is because I know you can do that part, right? Like, I know that that's just a replacement. This feels a little bit different. Yeah? You mean ever do you need the stack? For DFS, absolutely not. That's what we've done here. We're using the call function stack instead of an explicit stack. Exactly, okay? But you could, I mean, yeah, you definitely could. Everywhere you had a queue function in breadth first traversal, you could replace it with a stack and it would work fine, okay? All right, any other questions about the right-hand panel there? Okay, let's talk about the left-hand panel by way of review, because this is really, truly cut and paste, except I changed this word. Okay, so I want to know, by way of review, what this left panel is all about, and I kind of expect two different answers. Do you remember what's going on? Initialization is for that first one, exactly right. We have to set things up for the traversal. And how about the second one? Yeah? Yeah, very good. I'm going to give you a different word, components. We're going to make sure that we traverse all the components in the graph. Okay, so this is initialization. And this is reach all components. I have a quick question for you. This is also by way of review. Suppose I were to modify this function to see if a graph had a cycle. How would I do it? What would I do to modify this to check to see if a graph had a cycle? Where? Who's talking to me? That's right. If a back edge exists, that indicates more than one path between a pair of vertices, okay? And as such, that characterizes a cycle in the graph. So what we would do is simply yell right here, hey, there's a cycle in this graph, and that's it, okay? Any question about that? All right, and then I'm not even going to say it, but like last time, we could very easily modify this so as to count components. And I'll let you go look back at last time's lecture if you wanted to do that, okay? I guess I did say it. Any questions about all of this? Okay. I'm not going to do this example because I think you could do it. I think you could do it without me. What we are going to talk about is the analysis of this thing. So without trying to think about this very deeply, what do you hope is the running time of depth first search? Big O of M plus N. Good, very good. That is that we're pretty sure that we're going to have to look at all the edges and all the vertices, okay? Duh. But let's see if we can justify it. Now, yes? I know. My intention is that that's hanging out there. So, like, I'm not committing to M plus N yet, and so I'm not going to put it in a better color yet because I'm not ready to commit to it yet. Okay? No, that's okay. It's perfect, actually. It allowed me to say those words, so that's good. All right. I can't even see it. What are you talking about? There's nothing here, right? Okay. All right. So the analysis of this is a little bit different than what we've done before because the recursive calls, yes, they act on smaller subproblems, but we don't know the size of the subproblems, right? Because here our recursive calls are simply making a call on the kind of the next chunk of the graph. We don't know how much of the graph is left. So it's not like we can say, oh, this is DFS of n over 2 or something like that, right? We aren't dividing it in half. We don't know what we're doing. We don't know the size of the subproblem. So rather than try to write down a recurrence, what we're going to do is look at what happens over the course of the whole algorithm. Okay, the whole algorithm. Let's see. So all that happens in traversal, we set a bunch of labels and we look at we query the structures to see what their labels are. And we make these recursive calls, okay? And that's it. Now, how many recursive calls do we make? It's a little hard to think about, right? At most. Give me an upper bound on the number of recursive calls we make. Yeah, that's right. It's 1 per vertex, right? You're only ever going to traverse from a vertex 1 time. You're going to call DFS from a vertex 1 time. Okay, so that's an order n number of things, each of which does some of this stuff. And that's it. That's all it does. And evaluates conditionals, but those are queries, right? Like those are what to do if a label is a particular value. Everything, constant time. All right, so every vertex is labeled twice. Once when we initialize the graph, and once the first time we see it. And that's it. So over the course of the algorithm, that uses order n time, the actual changing the labels themselves. We'll talk about querying those labels later. Every edge is also labeled twice. First to initialize, and then to set it to either discovery or back. It'll never be twice, and furthermore, once it's labeled, it's never relabeled. The label is never changed. There's never additional computation to change the label. So this is big O of M, okay? The only other thing that happens is this kind of looking across the graph at neighboring vertices. Now, I want you to think about this vertex over here, okay? Will you come stand here for a second? Okay, just stand here. Okay, thank you. Just stand there. You're a vertex. You can face your crowd if you want to, okay? You're a vertex. Now, all of the adjacent vertices are going to go, yo, have you been visited yet? To which you might reply, no, right? Only 1 time. Are they ever going to say no? Because the second they say no, I'm going to change the status. We've already accounted for that cost. Now, the question for you guys is, how many times does that vertex get asked their status? Yeah? Yeah, exactly. So it's all the incident edges or the adjacent vertices that are eventually going to query that vertex. And so we know the amount of processing that happens of querying is degree of the vertex for every vertex. Okay, thank you for being the vertex. If there were a Vertex of the Year award, you would get it. All right, so every vertex is queried degree of V times, okay? Or the total over the algorithm is this. What is that? 2m, very good. So that querying is big O of m. All right, and then querying the edges. Oh boy. How often does each edge get asked its status? Twice is exactly right. Once for each endpoint, right? Every edge will get asked, hey, have I been there before? If the answer is no, it gets marked. And then the only other time it's asked is on the other endpoint. It doesn't get asked more than once. All right, so this is big O of m as well. When we add up all of that, because there is no multiplicative factor here. We don't query once for every time we label. We just label a constant number of times. So when we add those up, we end up with m plus n. Now, like before, remember how to read this. This is dominated by m if there are a ton of edges, and it's dominated by n if there aren't very many edges. Okay? All right, any question about this? All right. So I want to keep going here with our next topic. Our next topic is so we're done with traversal, though a couple of the other algorithms that we look like will feel a bit like traversal. This one, the first one, not so much, but later on. There isn't much later to later, but it's true. We're not anywhere near close to being done. All right, so this begs a story. So imagine that there is a community somewhere, not unlike the one I grew up in, where the streets in the community are not paved, okay? And the poobahs of the city want to pave it. They want to make it so that people's feet don't get muddy when they walk around town. But the children in the town want a swimming pool. So this is a community disagreement about using resources. Well, let me tell you some of the constraints on the problem and see if we can solve it, okay? So this community has $30 million, okay? And each of these paving blocks, including a bridge, take $1 million to pave, okay? And swimming pools cost $6 million. Now, here's where the children were quite clever. They observed that the objective is that any pair of people in the community can walk between each other's homes without getting their feet muddy, and it doesn't have to be a direct route or the most direct route. So, on a small scale, take, for example, just these 3 houses. If I pave this road and this road, for example, I don't have to pave this one because this person can visit this person merely by walking around to get there. Okay? Any question about that? So the grand question is, can we afford to build a swimming pool? And the way I'd like you to answer the question, the way I'd like you to approach the question on this picture is I want you to develop your own scheme for deciding which roads to pave. And moreover, I want you to keep track as you do this of the order in which you pave the roads. So I'm going to ask you, okay, what was the first road you think we should pave? What's the second road you think we should pave? And that way, I'll be able to know kind of what your algorithm is. So go ahead and spend a few minutes determining for yourselves and for all of us whether or not we get to build a swimming pool. Anybody have a result yet? Yeah, so can we build a swimming pool?
Yes.
Can they?
Yes.
And is there any money left?
Yes.
$1 million left. Yes. What are we going to do with it? Okay. All right. So, yeah? What? 1 million left. Yes. So you can build the swim. You have 7 million left after building the roadways, and then you use up 6 of it to build the swimming pool. Yep. So I think 23. Is that right? 23. Is that what you got? $23 million to pave this city. Okay. So let's figure this out, okay? Let's talk about some algorithms. Now, every good algorithm needs a place to start, and I think none of you will disagree with me if I assert that this is a good starting place, right? Now, what I want to know from you is whether or not you, based on your algorithm, based on your solution strategy, whether you would have chosen this edge next or this edge next. Okay? Based on your strategy, not exactly what you did, because you might have started somewhere else, but based on your strategy, would you have chosen this edge next or that edge next? So, raise your hand if you would have chosen this edge next. Okay, raise them high. I'm going to need to see this. I want everybody to see it. Raise them high. Oh, okay, cool. I have a special name for you. You ascribe to Prim's algorithm for building roadways, and we're just going to refer to you as the Prim's Construction Company, okay? All right, so raise your hand if this is what you intuitively would have thought was, or in your algorithm, if this was a reasonable next edge to pave. Raise them high. I need to see. Okay, good. You are the Kruskal's Construction Company. Okay? Now, these are two, and of course I don't know for sure, but it's very possible that you would have a different algorithm that would result in these things. But there are very natural ways of making these choices based on these two algorithms. And in fact, they are the next two algorithms that we're going to talk about. Now, they are both what we call minimum spanning tree algorithms. We're going to talk about them in varied level of detail. But before we do this, I want to discuss just for a second why those are chosen, why those are the two that we study in this class, because there are others. Here's the thing. You probably, I'm not for sure, but probably came up with either one of these strategies on your own, just sitting here, just looking at the problem. I really love the idea that if you were born 50 years ago instead, that they could have, or 50 years earlier, these could have borne your names instead of these particular people. So, you know, that's kind of astounding to me. It's interesting to think about what things will bear your names and how your grandchildren or whatever that difference is will go, oh, well, that seems easy now, right? And it will happen for sure. Okay, so these, as I referred to, were our minimum spanning tree algorithms. We're going to look at kruskals first because it's consistent with the lab this week. Many of you may already have seen it even, and turns out to be kind of useful for MP7. Who knew? And then we'll follow on with prims, which is more of a traversal-based approach. Okay, so first thing we need to do is specify the problem. The input into the problem, into any piece of code that you use to solve the problem, is a connected, undirected graph with unconstrained edge weights. Now, what we mean here is that we allow negative edge weights. They still have to be weights. They still have to be things that you can add together. But in this case, we don't care if they are negative. Negative is fine, okay? And the output then is a subgraph. That G prime is intended to be a subgraph with the following characteristics. I'm going to give myself some labels here. If G is equal to VE, that is, if we describe the original graph by a vertex set and an edge set, when we're going to let the answer be G prime equal V prime E prime. And here are the constraints. G prime is a spanning subgraph of G. The spanning part just means that the vertex set is the same. So the implication there is that V prime equals, let's write the wrong thing. V prime equals V. It includes all of the vertices. Okay, any question about that? Okay, G prime, the G prime solution is also connected and acyclic. Connected and acyclic, a tree. Okay, one way of assuring that, we already know. Yeah, that's all I need to say there. So together, they get the spanning tree portion of the description. The minimization occurs in adding up the weights of all the edges that are chosen for this solution. So this is, G prime has minimum total weight among all such spanning trees. So what we're going to do by total weight, we mean we add up the weights of the edges where that E comes from the solution edge set. And we assume that this weight, this WE thing here, is a weight that's probably, if you're talking about implementation, it's probably stored inside the edge structure. Okay, so associated with each edge, you can have this little piece of data that constitutes its weight or its cost or its distance or any metric that you care about that's a measurement of that edge. And then if we're just talking about math, you probably have some function that indicates what that weight is. Okay, so based on all of that, Is the red subgraph here a minimum total cost spanning tree for this given graph? You think? How are you checking? Yeah? Yeah, you kind of go, well, let me see if I can do better, right? I completely agree. I completely agree. But there are theoretical notions associated with spanning trees that will give you nice algorithms to check to see whether a given one is minimum. One such theoretical result is, suppose you choose an edge that is not in the minimum spanning tree, it must be the case that it has weight higher than anywhere else on the cycle that it creates. So choose an edge, it will create a cycle, right? Choose an edge, it will create a cycle. That edge weight is going to be greater than any of the other edges on that cycle. So for us then, we can check and see, is this one greater than 2 and 3? Yes. Is 8 bigger than 2 or 3 or 2? Yes. Is 4 bigger than 2 or 1? Yes. So, we can't add a different edge to the structure and reduce the cost, okay? All right, so now here's another question for you. I'm going to reduce this weight. How far can I take it down before I change the minimum spanning tree for this graph? How low can it go? Could I replace this with 8 and not change the spanning tree? 7? Yeah. 6? Fine. 5? When I have 5, I no longer have a unique spanning tree, but the one that exists is still at least minimal. It's 4 that breaks it. The minute I take this down to 4, I no longer have, the red is no longer the solution, okay? There's one more little kind of intuition about these structures that I want to give you, and that is this. I'm going to change this 8 to 4. I'm going to ask you really quickly, does the minimum spanning tree change? No, it doesn't. Here's a common mistake that people make. The edge weights of the minimum spanning tree create paths through the structure. There's absolutely no guarantee at all that those total path lengths are in any way optimal. So you can see by looking at this example, it is much, much, much more convenient to go between B. If I'm trying to get from B to A, it's much more convenient to go through the 4. The minimum spanning tree doesn't promise that it's going to be a short walk between any pair of vertices. It only promises that such a walk will exist. Okay? Any question about that? So don't let yourself get confused by that particular point. All right. So let's spend just a few minutes talking specifically about Kruskal's algorithm. What I want to know from you before we start is, what's this? This structure. Yeah, it's a list of edges, but it's a special list of edges. What's special about it? It's an array of them. Good. What's special about that array? Yeah? It's ordered based on their weight. That's right. So I have created a sorted list of these things. Now, you might want to call it a sorted list. I'm going to call it this. See what you think. What do I mean by that? Priority queue, that's right. I'm going to call it a priority queue because what I'm always going to ask of this structure, whatever it is I'm always going to ask for the minimum next one. I can sort them ahead of time and throw that list up there because in the context of this algorithm, it's never going to change. The order of them is never going to change, okay? So I've sorted all my edges, I've thrown them up there, but really what we're doing is minimum, remove minimum from a priority queue, okay? All right, so here's how the algorithm goes. My priority queue is going to feed me the minimum total cost, or I'm sorry, the minimum cost remaining edge. In this case, that's AD. Should I include it in my solution? Should I? It's the best edge in the world. Should I include it in my solution? All of you, just go like this, okay? That would make me happy. Yes, you should include it in your solution. Go for it. Yes. Now, I'm going to make note of the fact that I have created a little teeny tiny piece of some solution by noting that A and D now have some path between them, right? Like A and D are connected. They are part of some larger structure, as part of some larger structure. Okay, and then I'm going to go back to my priority queue and ask for the minimum edge. It gives me EH. Should I add it to my solution? Yes, I should add EH to my solution. There's absolutely no reason not to do so. And I'm going to make note of the fact that E and H are now connected in the solution. That's the way to say it. How about F and G? The next one added to me, the next one handed to me is F and G. Should I include it in my solution? Sure, there's no reason not to. So I make note of the fact that they are connected. Now AB. Should I include AB? Yeah, I think I should, right? So I'm going to put them like this, and I'm going to put those all in a disjoint set. I mean, I'm going to group them together into a subset of the solution that isn't overlapping with anything else. Okay? All right, fine. What's the next one it gives me? BD. Should I add BD to the solution? No. All right, so here's how I'm going to check. I'm going to go, I just wonder if there's already a path between B and D. And the way I'm going to ask is simply, hey, B, are you connected to D already? And the way the answer is going to come is if they are already in the same subcomponent or in the same disjoint set of the graph, right? If they are, then I'm not going to remove the wall. Oh, darn it, I did it again. I mean, I'm not going to add the edge to the solution, okay? All right, so B and D, I basically just ignore it. Now let's look at G and E. I'm going to remove G and E from the priority queue. This time, I ask the question, are G and E already part of the same component of the solution? And I look at what parts they're in, right? Hey, G, what subset are you in? Hey, E, what subset are you in? In this case, they are not in the same subset. So what I do is add the edge between them to the solution, and I effectively take the union of their two subsets. Okay? Any question about that? All right, I'm going to do one more. Should I add GH? Should I add GH to the solution? No, because G and H are already, there's already a path from G to H. I should not add another way of getting between G and H. I'm making a cycle if I do that. Okay, so I'm going to stop here in illustrating the execution of this algorithm because I think we've hit all the salient points, and I want to ask you a question. How many of these edges will we look at? How many of these edges in my priority queue, all M of them, will we look at? Number of vertices minus 1. You want to say that. You all do. It's tempting, right? Because you know that only n minus 1 of those edges are really useful to you. But it isn't exactly true that you're really only going to look at n minus 1 of them. Because consider this graph. I'm going to add another vertex here. And I'm going to tell you the cost of getting between C and I is 1,000,000. It occurs down here, right? At the very bottom. And yet, it's one of the edges in every minimum spanning tree. Right? Eventually, I'm going to be including that edge in the solution. And that kind of thing could happen all the way through your algorithm. And so actually, no matter what, you're going to iterate over this structure to its end. Okay? You're only going to be, fussing with disjoint sets. Well, I guess you're checking every time, but you're only going to be changing the structure of your solution n minus 1 times, but you have to look at them all. Okay. Any questions before we go? That's it for today. We're going to analyze this next time.